Do you have any information about the analog lab?
Not yet. I think the analog lab will be started now. Today there is one particular link will be shared, I think, with you all for the slot, in-person slot, lab slot.
Well, I have not received that mail. I'm not sure if Satyam or Muthu have received it. I rather received a mail about the payment link. So I'll have to try pay.
Either
Yeah, sir, we haven't received it yet, anything regarding
okay,
labs,
so
except the payment.
okay, I will ask with the team and then I will inform you on Monday.
Yes.
Hmm.
So will there be
So
weekly assignments for labs as well, for which we'll have to
I
post
I don't
videos?
know. I don't know Gaurav, about it.
Okay.
Actually, the professor, one different professor will be taking, and TA will be handle this one all things. So I have no idea about it one. Uh, Probably on Monday or Tuesday we have any class now. So till Tuesday I will confirm and inform you. Okay.
Okay. Okay. Okay. So uh,
Now this is my
I'm not
circuit.
sure about the payment deadline as well for analog lab. It was mentioned as 11th, oh sorry, 4th November, but I think that was by mistake. So
Mm.
Yeah, sir, it's today.
today is the last day, is it?
Yes.
Okay.
But when you are getting a mail on with the 11th November, mm,
That was for payment for analog lab.
mm, actually I don't know about it. I will confirm you till Tuesday, but till now I am not confirming anything about
Yeah. Okay.
it. Okay. So yes. So your doubt is the consideration of the capacitor. Like this is our V naught, one resistor we are using, VB, RB, R1, and V1. Like this is my circuit. Okay. Now, with respect to this one, what I do, I required here the voltage is V1 plus VDD by 2. Okay. And at this point, what we are getting? We are getting the voltage at VDD by 2. Okay. With respect to this one, we are getting here the voltage is VDD by 2 minus VI. Okay. So basically to provide the extra voltage VDD by 2, what we do, either one way is that I put one battery here. Along with the resistor, I put one battery. Okay. This one voltage is V1, this voltage is VDD by 2. So we are getting voltage here is V1 plus VDD by 2. Okay. This is the one case. But what is the problem with this case, that we have to use two different batteries. One battery is the VDD, V1, one battery is VDD by 2. Okay, two batteries we require. Why? because at the this terminal we are required the V1 plus VDD by 2, and at this terminal we are getting VDD by 2. So we have required two batteries. One battery is V1 and one battery is VDD by 2. Now add these two battery and connect it with the negative terminal, sorry, positive terminal. Second thing, either connect this battery from here and either connect only VDD by 2 at a negative side also, not in this way, and in this way. Okay, so the problem is that we require two battery. So how we overcome this problem? We are in place of VDD by 2 battery, I am using the capacitor. Okay, I am using one capacitor. Now what capacitor do? Capacitor store the charges or capacitor store the voltage. So if this capacitor will store the voltage VDD by 2, so we only required one particularly battery for this purpose. There is no need of two different batteries. Okay, so this is the basic consideration why we use one capacitor. Now this capacitor is called the coupling capacitor. Any doubts?
No, sir.
Okay. Now there are some particularly conditions or some particularly limitation with the coupling capacitor is that, like if we are talking about the capacitor, so there are maybe possible that we have to decide which type of capacitor we are using, what are the voltage of that capacitor, what are the conditions of that capacitor. We have to define all these things. Okay, so this is the requirement when we are going to when we are going to use a capacitor. Now if we are talking about the what professor says that capacitor should be like that, the value of capacitor C should be set in a way that voltage storage time is high. And what is the meaning of voltage storage time? That means discharging time is high. Discharging time is high. Now, what is the discharging time? If there is one resistor and there is one capacitor, okay, so what is the discharging time of this capacitor? Yes,
1
what
by
is the
RC.
1 upon RC? So time constant tau is equal to 1 by RC. RC circuit series combination. Okay, so in the particularly RC circuit series combination, the time constant is 1 upon RC. Okay, now if this is the time constant 1 upon RC, so we have to set a time constant high. And how we set the time constant high? That means the value of RC should be less. Now, how particularly RC should be less? If and C both are less, that means either R is less or C is less. Okay, R is less, no issue. The value of R1 is less in our circuit. The value of R1 is less, so if operation amplifier, the gain of the voltage gain of the operation amplifier either RF upon R1 or 1 plus RF upon R1. Okay, for the case of inverting, for the case of non-inverting. Okay, now if R is very less, or we can say the R value is approximately 0. R value is approximately 0. So now what will be happen in this scenario? If R1 is very less or approximately 0, that means voltage gain should be infinite. Now, if voltage gain is infinite, it is not possible. It is not possible. Why? It is not possible because if the voltage gain is zero, sorry, voltage gain is infinite, that means my operation amplifier will be work as a uh, amplifier circuit, oscillator circuit, not amplifier, oscillator circuits. Okay, so the condition is that R value should be 0, but ideally R is not equal to 0. R is not equal to 0. And the reason of this one is gain is infinite. Okay, any doubts? Yes, any doubts?
We are discussing week 3.
Now, yes,
Are we discussing week 3 or week?
that is the part of week 3, no?
So yeah, you are discussing the coupling capacitors. Huh?
Yes, yes, I will go with that part also.
Okay.
Okay. Now, it is not possible that the value of R should be equal to 0 for getting the high time constant. So the second scenario is capacitor. So the capacitor value is approximately 0. If capacitor value is approximately 0 or minimum, the time constant is high. Okay. But ideally, capacitor value 0 is not possible. Okay. Capacitor value 0 is not possible. So we have to set a capacitor in a particularly condition that that time constant is increases as well the C is very less. This is the one consideration of the about the coupling capacitor. The value of capacitance is very less, so it will be increase the time constant. Okay, but at what particularly the minimum value of the capacitance we can set, we have to calculate this one also. So this is the basic consideration why we use the capacitor and what particularly things we have to remember when we are using this capacitor.
Sir,
Yeah,
we want the time constant to be large.
yeah.
And why would we want that to be the case? Means time
Because
constant to be large means the capacitor should discharge slowly.
capacitor should discharge slowly. That means the capacitor will be working as a battery.
Okay, okay, okay. And we want it to work as a battery because we want to make use of a single voltage source.
Single voltage source. In the single voltage source, either if we are not using the capacitor, so we have to require two batteries. One is for input signal battery like V1, okay, and second is the VDD by 2 that we connected at the both terminal, either inverting and non-inverting terminal. So we require two particularly batteries. To avoid these conditions, what I do, I just use one capacitor as a battery, and the voltage
So
it will be provided by the
besides
capacitor.
besides time constant being a constraint on the capacitor's value, does VDD, the value of VDD has got a role to play in deciding what value of capacitor should I use?
The VDD is that capacitor value. If I say the capacitor value, okay, if I said this is my capacitor value like 1 microfarad is my capacitor value. Okay. Now this particularly capacitor, how much voltage it will be stored? Like it will be stored the VDD by 4 voltage. Okay, that is the maximum limit of this capacitor to store. So how it is possible that using this capacitor, I am providing the VDD by 2 voltage? Is it possible? If any capacitor will provide maximum limit and that voltage is VDD by 4, so is it possible that we can use that capacitor to provide the VDD by 2 voltage?
No, sir.
Condition to basically define, remember when we are going to work on that. Okay, we have to set the capacitor who will provide VDD by 2 voltage. This is the first consideration to set the capacitor value. Yes, any doubts?
And
Sir?
regarding time, sorry, go ahead, Muthu.
Yeah, sir. You go ahead. Yes, so time constant is the product of R and C, right, sir?
Yeah,
Okay.
time constant is the
And it
product of R.
determines the okay. So and it determines the rate, the speed at which it charges and discharges.
Yeah, basically, if we are using any capacitor, like for example, if you heard the term of supercapacitor,
Yeah, sir.
okay. So basically, what supercapacitor do? The basically time constant, the value of the supercapacitor time constant is very high. So basically, that supercapacitor is
Yes.
most probably used for the battery purpose. Similarly, if you are talking about our Bluetooth devices,
So battery, using the battery is a different option, but most of the cases we are using the capacitor. Okay, so what is the reason behind using the capacitor is that capacitor is safe. If you charge that with a higher volt, basically if you are charging for a longer distance, it will be safe. Okay, whereas if we are talking about the capacitor is, there is some issue in the capacitor, like due to the heat up, due to the use of that particularly Bluetooth device for a longer duration, maybe your battery will be heat up and it will be damaged. Okay, so to avoid this one, what we do, we are using the capacitor as a battery.
Yes.
Okay, and if we are using a capacitor as a battery, so we have to set a particularly capacitor discharging time in a way that it will be used as a battery. Otherwise, what will be happen if you are using a capacitor, any of the capacitor as a battery? So you have to basically you charge the capacitor with the 100%, and after 5 minutes it will be discharged. Okay, again you charge 100% and it will be discharging for in 5 minutes. So there is no use of that capacitor to use as a battery. Okay.
Yes.
So how large this time constant should be? What will decide this?
That is divided. That is all decided by the value of R and C. Okay, we can't do it infinite. Why? Because to create a time constant infinite, my R value should be minimum and C value should be minimum. And if both values are zero, or maybe any of the value is zero, we can say our time constant is infinite. But this is not practically feasible. Okay, because if my R1 is zero, like I am using this one, if my R1 is zero, like I am creating one circuit here, my circuit should be like that. This is my operation amplifier. I am using one source here. Along with the source, I have RS. Along with that, we are using one battery for the add up of the voltage. At the negative side, I am using one resistor. And here I am using again the VDD by 2. This is the VDD and this one is the output. Okay, so if this is my circuit, I have to use this one voltage should be what voltage? That if that voltage is VDD by 2 plus VI. Okay, so we are giving the VI. This is my VDD. Okay, so we require two batteries. Now the second way is that I remove this particularly battery. In the place of this one, what I do, this is my V1 RS. I am using capacitor. This is the electrolyte capacitor, so this is the symbol of electrolyte capacitor. Okay, now if I have added one resistor here, this is VB, this is the RB, and this one is the RB and grounded. Okay, so if my RS value is 0, or C value is 0, I can say my time constant is infinite. Okay, or I can say Rs plus Rb by 2. Okay, that means this one and this resistance should be 0. Or the capacitor should be 0, I can say my time constant is infinite. That means the battery is very good because it never discharges. But what will be happen in this scenario? It is not possible that any particularly thing having a 0 resistance. Either if I am taking a pure conductor wire, the resistance value is always exist. Only one situation is available where the resistance value is not available. This resistance value is 0, and that is the effect is called the superconductor.
Sir,
But this is the property, yeah.
here time constant also should be 0, right?
Why?
R into C, so 0.
RC is 0 and time constant tau is equal to 1 upon RC.
Time constant is also RC, right?
Time constant we are taking 1 upon RC. This is not 1 upon RC. Yeah, time constant R is also, sorry. So time constant is RC. Now if R is C is infinite or time constant is R is infinite or time constant is infinite. Okay. These two resistance value is infinite or the capacitor value is infinite, we can say the time constant is infinite. So ideally it is feasible. It may be feasible, not it is, it may be feasible. But practically feasible. Practically not feasible. Why not feasible? Because if Rb by 2 plus Rx is infinite, that means current is 0. Okay, and if capacitor is infinite, so the capacitor is infinite, my voltage storage is 0. Okay, my voltage storage is 0. So voltage storage is 0. So in this case, what I do, I have to create a handshaking condition. What is the meaning of handshaking condition is that I have to choose the value of R and C in a way that time constant is high, similarly the value of R and C can't be equal to 0. Okay, so this is the handshaking condition. We have to set our time constant values to high, but we have to choose the value of RC that should not be equal to the infinite. So for this, what we do, if I am taking a circuit, so my circuit should be like that one. If this is a VI, RS, capacitor, Okay, and the resistance, that is RB by 2, and here we are getting a VDD. Okay, we are taking this one Vx. Okay, so this is my circuit that I am using. This is grounded, this is grounded. Now, if we apply the output upon input, so what is the output Vx? That is the voltage drop across this one. Multiply by the I. And what is input Vi? That is the current flowing through this circuit. Okay, so Z multiplied by the I and I cancel out, so the value of Vx upon Vi is Rb by 2 upon Z. And what is the value of Z? 1, 2, and 3 component. And all three component are in series. So can I set is Rs plus Rb by 2 plus, due to this one, 1 upon Cs. Okay, so Vx upon Vi should be equal to Rb by 2 upon Rs plus Rb by 2 plus 1 upon Cs. And now if I am taking the LCM, so what is the value? Vx upon Vi, Rb by 2 upon 2 Cs, that is Rs, 2 Rs plus Rb multiplied by Cs plus 2. And 2 and 2 cancel out, so it's remaining the Rb times Cs upon 2 Rs plus Rb times Cs plus 2. So this is the output upon input voltage. That is basically at the point of input side of the operation amplifier at this point. This is the Vx. This voltage. This voltage is Vx. Okay. Now if you solve it furthermore, so Vx upon Vi is equal to, again there are the several assumptions. Like first assumption is that Rs and Rb are infinite. Cs when I am taking the Rb common, so remaining is 2 Rs upon Rb plus 1 times Cs plus 2. Okay, this is the first scenario. Cancel Rb with Rb. Okay, if I am taking the capacitance value will be infinite. So Vx upon Vi is equal to Rb times Cs upon 2 Rb plus 2 Rs plus Rb, Cs from common here, plus 2 upon Cs. Okay, and Cs cancel out, or S and C cancel out.
So Vx upon Vi is equal to Rb upon 2 Rs plus R. And this component is 0. Why? Because capacitor is infinite. So 1 upon capacitor infinite is 0. So the value is 1 upon 1 plus 2 times Rs upon R. Okay, so this is the voltage that we are getting at the input side of the operation amplifier Vx when we are applying the Vi. If capacitor is infinite. But as we already know, it is not possible that capacitor should be infinite. Now, what I can do with this? One more thing is there. If I apply that, if Rs is less, series resistance of the battery, input battery. Okay, so Rs is less than. So Rs is less than RB. So my output voltage Vx upon Vi is equal to 1 upon 1 plus 2 into Rs upon Rb. Now Rs upon Rb is less than 1. So 2 Rs upon Rb is less than 1. That means 1 plus 2 Rs upon Rb is approximately equal to 1. That means Vx upon Vi is equal to approximately equal to 1. So there is no change. There is no change. Why? Because we assume the capacitor should be infinite. So we can't set the capacitor value is infinite. We can't say the capacitor value is infinite. Now then what will be happen? So we have to set it reason that now what we do is if this is either I can calculate the frequency also with that. So if you are going to calculate the frequency, so what you can do here, so Vx upon Vi that is equal to Rb by 2 upon Rb by 2 plus Rs plus 1 upon Cs. So I can use this consideration like if RS is less than RP. So we can say that Vx upon Vi is equal to RB by 2 upon RB by 2 plus 1 upon Cs. So the value is RP upon RP plus 2 upon Cs. Okay, like if I'm taking the Cs as LCM, so RB times Cs upon RB times Cs plus 2. Yeah, if I take a magnitude of this component, so Vx upon Vi component, that is equal to the numerator part RB into C into S is j omega upon 2 plus RB into C into j omega. Now, how we take the magnitude of this one? If only the real component, we can take the magnitude. If it is only an imaginary component, we can take the real magnitude. If we have a complex term, that means combination of real and imaginary, what we do is square root of real component square plus imaginary component square. So if I take the magnitude of this one, so it becomes RB into C into omega upon root of 4 plus RB square C square omega square. Okay, this is the scenario when C is not equal to infinity. Capacitance is not equal to infinity. In the previous scenario, when capacitance should be equal to infinity. Okay. Now if I want to set a magnitude of this one as a 1, so how it will be set? If I take a consideration that this parameter is greater than this one, so the addition of these two is equal to RB square C square omega square. So what I consideration here, that RB square C square omega square is greater than 4. That means that implies 4 plus RB square C square omega square, that is equal to RB square C square omega square. Okay, and if I take a square root of this one, so it becomes RB into C into omega. So when I put this value in this one, so Vx upon Vi is RB into C into omega upon RB into C into omega. Remove this one, that is equal to, okay, but this one is only considerable when RB square into C square into omega square should be greater than 4. Okay, Now if I calculate the value of omega f, so RB into C into omega should be greater than 2. Take a square root, so omega is equal greater than equal to 1 upon RB multiplied by C. Sorry, 2 upon RB multiplied by C. Okay, and F is equal to 1 upon pi into RB into C. This is the frequency. Okay, this is the frequency. I think in your video, when I see, it should be like professor will be calculating the Vx upon 2 Vi.
Yes, sir.
Okay. So that value is equal to the, if we are taking the Vx upon 2 Vi, I think that value is equal to 1 only when RB into C into omega should be greater than. Okay, I think they are considering some other part of this one, but I am taking simple. So how we consider the value of capacitance in our circuit? Okay, so in this way, if you are getting the value of f should be greater than 1 upon 2 pi r dx. Okay, and the professor will be getting this one. Okay, and we are only taking this circuit without any assumptions, like I have to see that what professor tells, but professor will be using this one. Okay, so this is only about that how we calculate the frequency component. Now what is the meaning of this frequency component? Yes, what is the value of this frequency component?
The capacitor will be considered very large till that frequency, or or for those frequency which
Basically,
satisfies.
yeah, exactly. If this f is we have calculated, like f is 10 kilohertz. Okay, in this scenario, capacitor effect is considered. Capacitor effect is considered. So this is the frequency range. Like if I am supplying any Vi signal, Vi that is a AC signal. So it is just to remember that the value of f frequency in a AC signal should be 1 upon 2 pi r. Either it is greater than or equal to. Generally we are taking the greater than. Okay, so f value should be considered in this way. Okay. Now the second thing that is arises that what is the maximum value of capacitor? Maximum value of the capacitor. So again I am taking the same circuit. This is RP by 2 RS C and V. VI. So for this I have to apply a Thevenin theorem in this one. Okay, and according to this Thevenin theorem, what should I do? I have to take this VI voltage as a VTH. Okay, the RS and RB combination is RTH, and I am using one capacitor. Okay, so I have considered this particular circuit as a Thevenin's equivalent. Now we have to set what is my value of the capacitance. So first thing is that capacitor will always pass the AC signal. Okay, capacitor will always pass the AC signal and it will block the DC component. Why it blocks? Because the impedance admittance, so basically capacitance is 1 upon j omega c. So if f is 0 for the DC signal, 1 over 0, that becomes infinite. That means for the DC signal where frequency is 0, capacitance value should be infinite. So it will be not allowed to pass anything. Okay, and for AC signal, it will be allowed to pass everything. Now, what we do in this case, we have to calculate the value of C by using some consideration. Now, if I say that this voltage is VC, so what is the voltage is VC? Yes, what is the voltage is VC?
1 by j omega c divided by
Directly,
RTH.
I say that the voltage drop across this one is the V. Okay, so VC is nothing but VTH minus V1.
Yes.
Okay, the voltage drop across this one minus the voltage drop across this one. Now, if I want to calculate the voltage drop across this one and the impedance value of this one is 1 upon SC. So the voltage drop is VC is equal to VTH into SC upon RTH plus 1 upon SC. Okay, that is equal to VTH into 1 upon 1 plus RTH into SC. Okay, now capacitance. Yes, so the if capacitor value is maximum, if capacitor value
Sir,
is maximum, yes,
here are we using S as a uh,
1 upon
variable
S is
for
equal to j
j
omega.
omega?
J omega. Okay, S is equal to j omega. So the if the maximum capacitor value is high,
C is equal to QV. Okay. So for the high capacitor value, my voltage should be 0 because the capacitor is 0. Minimum, or we can say the 0. So what I do, we have this voltage source across the, we have this voltage across the capacitor, and for a high capacitor, this value, which value? VTH upon 1 plus RTH SC should be approximately 0. Okay, this value is 0, capacitor will be. Now if this one will be 0, so VTH upon, if I'm taking the magnitude of the denominator term, so 1 upon RTH square into S square into C square. Okay, and this value should be equal to that means 1 plus RTH square into omega square C square, that is very high, that is greater than 0.
Sir, why we have the square root term?
Magnitude,
Oh, okay, yeah.
1 upon RTH omega square. Okay, S is j omega. So if this one is true, so VTH upon 1 plus RTH j omega C. Okay, and we have to take the magnitude. So for the magnitude, we have at the denominator side, we are taking the magnitude by putting the formula that square root of, for the complex value, the magnitude is square root of one real component plus imaginary component square. Okay, so that's why I am taking this one. Now, how this value should be 0? If this value should be 0 when denominator will be infinite or very high. Okay, and if denominator will be high, so 1 plus RTH square omega square C square should be greater than 0. That means RTH square omega square C square should be greater than -1. Yeah, and with this, if we calculate the value of C, so what is the value of C? RTH square should be greater than 1 upon omega square C square. So RTH should be greater than 1 upon omega C. Or we can say 1 upon C should be less than equal to omega times RTH, or C should be greater than 1 upon omega R. This is the consideration of capacity value.
Okay,
Sir.
this is the consideration of the capacitor value, coupling capacitor value. That the value of C should be greater than equal to 1 upon omega time RT.
Sir, here where does this minus sign go?
The minus sign will be goes because if you see that this is the multiplication of three components RT, omega and C. Okay, and the
Yes.
value of these three components is positive. Either I am taking the
Correct.
capacitor, either I am taking the resistor, and either I am taking the frequency. So should I put it in the form of magnitude? So mode of RTH square, omega square, C square should be greater than 1. Okay, that's
Yeah.
why I am neglecting this one. Okay.
Sir, in the lecture, I think the professor has used directly the square root of 1 plus RTH square omega square C square is greater than 1 instead of 0.
Yeah, yeah. Where this one,
Uh, where, sir?
you are asking that 1
Mm,
plus RTH square omega square C square should be greater than 1.
mm, yeah, yes, sir.
No.
Great. No, no, no. The directly it go. Yeah, he came directly to the step instead of
Yeah, they are not
showing
taking
the
this one
place.
minus 1. They are not taking this one minus 1.
Yeah,
They are
correct.
putting this one,
Yeah.
and after that, they are writing down this one directly.
Okay. So these are the intermediate steps which are not shown in the video.
Yeah, actually, it is basically they are understanding that you know this thing why this will be happen.
Okay. Hmm.
That's why they are basically okay.
Okay.
But the value of RTH, omega, and C value is not possible that any value will be negative. The value of capacitor should
Correct.
be positive. Okay, polarity we can
Yeah,
change,
yes.
but the value of the capacitor should be defined in the positive.
And sir, why we have take 0 on the right hand side in the first place?
Uh,
Because any positive number,
this one,
I mean, any number can be.
this one.
Yeah, yes.
Okay, actually,
Yes.
if you see that capacitor QC is equal to Q by V.
Yeah, yes.
Okay, if I have to maintain that capacitor value should be greater than, or basically the value is higher. Capacitor value is
Mm.
higher. So what is the condition of that one? The voltage value should be 0.
Low. Yeah, yes.
Okay. Now, how should we put this voltage value should be 0?
Okay.
If the denominator term is infinite.
Yeah, I mean,
Okay.
yeah, in denominator is 0, right?
Denominator is infinite. Then this complete term should be
Yeah.
0.
Yeah, yes. C goes to
This
0.
is this is the value of VC. Wait a minute. If we are talking, this is the value of VC.
Yeah, yes.
Okay, we have calculated here, no?
Yeah.
VC value. This is the value
Mm,
of VC. Then how
yes.
capacitor will be? How the value of capacitor will be infinite but large? C value will be higher only when V value should be lower.
Yeah.
Okay. If V value, if I have
Yes.
assumed that the capacitor value is infinite only when the voltage should be zero.
Correct.
Okay. Now, if voltage value VC is equal to VTH upon 1 plus RTHSC. Okay. So if I take the magnitude of this one, so what is the magnitude? The numerator term magnitude is VTH.
The denominator of magnitude is 1 upon RTH square into omega square into C square and root of this.
1 plus.
Okay.
Yes. Square.
Now this value should be 0 when the
Denominator just 1.
denominator is very high or infinite. Okay. Why? Because VTH is 0, not possible. It is not possible. So we have to set that denominator should be infinite
Very
or
high.
the higher value. Basically, the higher value, not infinite. We can't set the
Yes.
infinite value, but higher
Infinite.
value. So if the denominator is higher, voltage is lesser. If voltage is lesser, capacitor is higher. Capacitance is higher.
Oh. Yes.
Okay. Now, if denominator is high, so should I put this one 1 upon RTH square into omega square C square? The root of this one will be greater than 0.
Okay. Yeah. Yes.
Okay, so we are setting this value. So
By this
according to
we
this,
mean that the left hand side is very large.
yeah,
Mm. Yeah. Yes.
the capacitance is very large.
Mm.
Okay, and capacitor, why capacitor is large?
So that it allows most of the
Time
AC
constant
voltage.
is infinite.
And sir, when the time constant is very large, like say infinite,
Mhm.
it will
Yes.
take. I mean, we can't charge it, right? Because it will take infinite time to charge.
Yeah, time, infinite time to charge and infinite time to discharge also.
Yeah. So when it comes to charging, um, so what we will it be anything? Will it cause anything not desired
No, no, it
since
is
it
not.
is so long?
Actually, for the charging, if we set the charging and discharging time, so basically it is also dependent on the current that is going inside to charge that. So if on charging and discharging time is higher, so what I do, I am using the high power circuit or charging system to basically charge it very quickly. And after it will be charged, it will be take longer time to discharge.
Okay.
Okay.
So
Like if you are saying
we
that
can.
there are two types of cells are available. If you compare, I don't know, a normal ordinary cell, pencil cell, and one is the Duracell cell, pencil cell. Have you
Yeah.
noticed any difference between them?
Yeah, it claims to be durable and long lasting.
Yeah, long lasting and durable Duracell cells. So why?
Uh,
Because their time constant will be set in a way that they provide the current for a longer time, provide the voltage for a longer.
mm, okay. So we can make it charge faster also, even though the time constant is very large.
Yeah, we can change. We can do that.
Okay. Yeah.
So providing the higher current. Similarly, if you have
Yes.
a high power batteries in your mobile phone, and you are
Hmm.
right now, if you see that there are 5 or 10 watt charger are available, then 20 volt, then 30 volt, then
Yeah.
60
Faster.
watt charger, 74 watt charger. So you are increasing the power of that one. So your capacitor or battery will be charged fast.
Okay. Yes.
Yes. Yes.
And sir, likewise, in the same lecture video,
Mhm.
in the
Yes.
ending of the video, I have one doubt in
Yeah.
calculating the RTH,
Calculating
the Thevenin resistance.
okay.
Yeah. So in
I
that,
think sir are using one circuit. Not talking about
yeah,
that
yes, sir.
circuit.
In that circuit, I'm little confused how the RTH comes to be that particular value. Could you please derive it once, if possible?
Wait a minute, I just check what is the circuit because I don't really know. Circuit is the circuit professor are taking is VI and K fifty K 5 volt VI C1 volt down C2 1. Okay, so if this is a 5 volt, let a positive terminal. So this particularly voltage is also a 5 volt. Okay. Now, if this is the 5 volt, so we can say uh, 5 volt is there. So I can say VI minus 5 volt upon 20K plus 1 upon 6. This is the current I. Just any doubt?
Sir, how can we say that the input, the Thevenin resistance is 20K?
Yeah, I tell you. The Thevenin resistance across the capacitor C1. Okay.
And so if I'm talking about this capacitor, this according to this one. So the input side is at this point. And how many resistors are connected?
2 resistance.
Two resistors. The value of two resistors is 10k plus 10k. So R is equal to 10 plus 10 is equal to 20.
Sir, if they ask Thevenin resistance, we have to just disconnect the capacitor and across the two nodes we have to just find out, right?
Capacitor is basically what it is if we are considering that capacitor behave as a voltage source. We
No,
see this.
we are finding the Thevenin resistance across the capacitor, right?
Yeah, across the capacitor. So uh,
We open the capacitor and short the Vi. Then we have one side, yeah, ground, and the other side 5 volts.
yes, yes, yes.
Should we make it as a battery and short it once again?
Exactly, and I think that capacitor is considered. It is not considered. Yes. Okay.
So, sir, in this case, we consider the input impedance offered by the amplifier is 0. Is it?
Input impedance offered by the amplifier. No,
Then, like, we are just neglecting it.
no, no, no.
Then, what are
How
we
to
considering?
complete?
Hmm?
So we are just neglecting the amplifier here.
We are not neglecting the amplifier. We are talking about the actually the similar scenario, na? Like if you are talking about this scenario. So what we consider the RTH? These two resistance effect.
Yes, sir, but they are completing the circuit, right? I mean, it forms a closed circuit.
Here at the
So,
other
like
end, we
this.
are having it as floating.
If the if the potential difference at these 2 points, this point and this point. So can I consider the difference between these two as a grounded?
This one. If they are saying that the across capacitor, okay, so capacitor behave as a voltage source. If capacitor behave as a voltage source, so what I do, I have to convert it to the short circuit. So the circuit should be like this is the 10K, this is the 10K. So what is the value of current? I is VI upon 20. And this 20K is basically the RTH. They are not exactly taking across the capacitor, they are basically calculate the Thevenin equivalent inside at the input side.
But sir, anyhow, mm, make we remove the capacitor and go from the one end to the other end and find the
Yeah,
RTH.
basically, wait a minute. If you see in the particularly this question, you can see one thing here is that professor will be put the voltage at across this capacitor. And what is the voltage he is putting here 0 and here 5.
Yeah, yes.
Okay, so why they are putting this one? That means the capacitor they are working behaving as a battery or supply voltage source.
Sir,
That's why
left
they are
side,
putting this one.
the left side, is it 0 or VI? Or?
Across the capacitor, if you see that the voltage they provide is 0 and 5 volt. Why?
Yeah,
Because
the 0 is a
capacitor.
VDC component, a DC
No,
component of the.
no, not exactly. Basically, your capacitor you are using for the VDD by 2, for providing the VDD by 2. You are using this capacitor because it is a single supply operation. Hello.
Yeah, yes, sir.
It is a single supply operation. So single supply operation, what we are providing here, this is the VDD by 2,
Yes, sir.
and the input voltage is VI plus VDD by 2. Now VDD is 10 volts. Okay, so that means at the input side, what I should provide? VI plus 5 volt. Now, if I provide the VI plus 5 volt, that means this capacitor behave as a 5 volt battery, where one terminal, negative terminal, behave as a 0 and positive terminal behave as a 5 volt.
Yeah.
Okay, so that's why they are putting 0 and 5 because they
Yeah.
are using this capacitor as a VDD by 2 supply. This is VDD by 2 supply source, not a capacitor. Okay, now if it is a supply source, so I want to take a Thevenin equivalent Thevenin, so what I do? Just short, and total resistance of the circuit will be the Thevenin equivalent. Okay, so if I short this one, so these two particular resistance 10K and 10K are in series, so total resistance is addition of these two, and that is 20k. That's why they are taking the 20k.
Okay. So
Okay.
in the right hand side, we can extend this 5 volts to the ground. Is it, sir?
And the right hand side,
Yeah, the diagram which we have drawn at the bottom.
yeah. Mm,
So for
Where
completing the
you are asking at this point, or you are asking some other point?
um, the diagram below.
Yes, diagram below. So
Yeah.
here what I
So
do,
for
this is the
completing
VDS.
the circuit,
Yeah,
we
this is a
can
circuit. So the current going,
connect the
no, till this point, what we are getting the current value is VI through this resistance. The value of current is VI upon R TH, and the value is VI upon 20k. So that's why we are on oblique R equivalent, not I am giving that the RTH R equivalent. Okay, and that R equivalent is 20k. So my R equivalent value is 20k. But if you see in the input side, there is no other circuit, no other particular resistors are available. So this R equivalent is also equal to the RTH. If we are taking as a common short circuit, a virtual ground condition, again this terminal will be at a zero potential. The difference between these two terminals is as a zero potential. The difference between this terminal and this terminal is zero potential. That means the resistance is zero. Resistance is zero. That means we are using that it is similar to the ground condition. Okay. So the voltage drop between these terminals is zero. That means this resistance voltage drop is zero. So it is similar to the ground condition.
yes. Mm,
Okay. So in this scenario, we can say that this particular circuit is completed, but not exactly this one. What we are doing, we are just calculating the current value, and in the current value, the value of resistance is just equal to the R equal or RTH. That's why they are taking the 20k in the input side, and similarly for the output side, if you are talking, again there is a capacitor at the output side. What we do with the capacitor, we just short this capacitor. Okay, so if we short this capacitor from this point to this particularly path, only 1 kilo ohm resistance is available. So it is the R equivalent at the for the C2 or RTH for C2. Again, if you are talking about the circuit is not completed, so how we say that this is the RTH?
do we have ground on the output
We
side?
have the
I mean, the
ground at this point, but we don't have this particularly. This is the ground point. So how can we say that the circuit is completed? But if the current is flowing from this way, this
we
resistance
have the
only,
ground inside of the op amp, right? In the output side.
inside the op-amp, the output side, the equivalent is like that one.
No, sir, the ground
One
inside the op
resistor,
amp.
then there is one particularly this one, and this is the ground. Okay. But this point is not a ground. This point is not a ground. This point is ground, but this point is not ground. Now it will be connected with the this resistance and this ground. So how we can say that the circuit is completed? Okay,
Yeah,
but
because we
the current is going from this resistance is what V upon 1k. So this 1k is overall equivalent resistance, and we tell them that this is the due to the voltage source, so it is equal to the RTH. Okay.
so sir, like for completing the second diagram, can we just put ground on the 5 volts or make it look like a battery?
No, but we are saying that the current will be flowing now. Current is flowing through this particular part because here we are saying that if it is a Gaussian surface, so the direction of current will be going in this way. If the current is
Okay.
going, that means circuit is completed. That's why current is going. Otherwise, why current will be flowing?
Okay. So the current is flowing from right to left, sir?
Yeah.
From 5 volts to
So,
ground.
uh,
Because we are shorting VI.
yeah.
Okay. Yeah.
If we are saying in the left hand side, if we are saying that this is my VI, this is my VI, this is basically behave as a 5-volt battery. Okay, so this is the direction of current. Okay, now if current is going, that means my circuit is complete because without circuit completion, current is not possible to flow.
Hmm.
Now, if circuit is completed, what is the equivalent resistance? 20K. Okay, and we can say
Yeah.
that this particularly is equivalent to the RTH. Why? Because we are fulfill that condition that my capacitor, my other voltage source should be short. So the overall resistance should be this one. If circuit is not completed, or we can say the current is not flowing, then we have to check that what is our basically condition to complete the circuit, or what is the basically after that what is my equivalent resistance or Thevenin resistance. But here we know that the current will be flowing. The circuit is ideal, the current will be flowing.
Sir.
Yeah.
And likewise, in the same video, just before this example,
Mhm.
um,
Mhm.
yeah, there is this derivation Vx plus a cos omega t plus phi
In what
divided
question?
by uh, yes, sir, in the same lecture video, just before this example diagram.
Bx plus a cos of omega
A
t
cos
plus
omega
phi.
t. Yeah.
Yeah.
So here, how we get the second term?
Actually, basically, we are using one Vi plus Vdd by 2 at the input side,
Yeah, is
where Vi is what? AC
the
signal.
AC input.
And
Yes.
Vdd is what? Vdd by 2 is DC.
Mm.
Okay. So that's why what we do here is that I am when I convert into the VTH. Okay. So when I'm going to convert as a VTH, so VTH is nothing but the addition of AC supply
Yeah, and
plus
DC.
DC supply. Now what we are saying that AC supply will be pass through capacitor and DC supply blocked by capacitor. Now I am assuming that my AC supply is what is the value? AC cos of omega t plus 5. This one? For any value, I can take a in a sinusoidal form. So AC sine of omega t plus 5. Okay. And why this 5 factor is there, right? Because
Phase shift.
my because yes, my circuit is not a pure resistor. Okay. There is a effect of capacitor
Yeah, okay. Correct.
or inductor. So that's why I take a phase shift that is 5.
So in our case, it should be capacitive, right, sir?
Yeah, in our case it should be capacitor.
So phi should be positive or negative.
Hmm?
If it is a capacitive circuit,
Yeah.
the symbol of phi.
And the value of phi is, if I'm taking the value of phi, the value of phi is 10 inverse xc by r, or the 10 inverse 1 upon omega c r. This is the value to calculate the phi angle phi. You have
Okay.
already studied. You have already studied. If you remember that there is a phasor diagram, RLC circuit phasor diagram,
Yeah, yes.
EC and ESTC. I think.
E.
So, due to because of this phasor diagram, you can calculate the value of phi. It is a positive or negative.
Okay. Yes.
So whether we will wind up here.
Yeah.
Or any
So
other
sir,
doubt?
could you please once derive it the second term just alone?
Which one?
Just the second term of the Vx plus A cos omega t. I mean, why we are dividing it with 1 plus omega square? Or
Actually, yeah. What is the value of this one is that I just calculate a Thevenin circuit. So what is my Thevenin circuit?
yeah,
One VTH,
the
one
mm,
RTH, and
yeah,
one capacitor.
capacitor.
It is known that it is- okay. The value of RTH depends on
Rs plus RL.
RB, RB and RS, or RS plus RL. That is the value of the circuit resistance that is available in circuit. Okay.
Yes.
So every resistance will be, with the help of every resistance, I can calculate the RTH. One capacitor is there and one VTH is there. Now the what is the voltage across this capacitor?
Yeah, when only DC is present, it is Vx.
Yeah. And when AC is available, it is VTH AC component upon, sorry, into 1 by CS upon R plus 1 by CS.
Okay.
Yes,
Yeah,
any
yes.
doubt? So it is
No,
a
sir. Yeah.
VTH AC component into 1 by CS. If I take the RCS LCM, CS LCM, so RCS plus 1 upon CS. It will be cancelled out. That will be remaining VTH due to the AC upon 1 plus R. I am putting the RTH, not R, RTH into C into SS, j omega. Now I have to take the magnitude. So what is the magnitude? VTH, that is intensity, upon root of the real component 1 plus imaginary component per square. So R TH square
TH
into
square,
C square
T
into
square,
omega square.
omega square. Yeah. Yes, sir.
Okay. Now
Yeah,
after
yes, sir.
that you know that we have to put this value, voltage value will be minimum. Why minimum?
Mm.
So capacitance will be maximum. Why capacitor maximum? Because time constant will be maximum.
So the previously we just need to do the one which we did previously, right? Omega C R T H is very greater than 1.
Mhm. We have already done this one. Okay.
Yeah, yes, sir.
Sir,
So, yes.
sir, which book to follow? Preference?
You can take a microelectronics book, any book, microelectronics or operation amplifier. There are lots of books are available on internet.
So,
Okay. Maximum topic will be covered in that. Some topics is not covered in book. Uh, there are lots of books are available. If you just
sir, I
message
have
me,
boiled state
I
book.
just
I use it.
yeah, Boristat you can use it. No issue. Minimal Healthcare is one book. Naeem is the one book, and if you basically if you either you can drop a message to me on the G space, I will put some books, PDF books are available. I will share with you.
Okay, sir. I will message you. Thank you.
Yeah. Okay, and till Shanti Pawan sir will be covered week 7. So till that you will find out all particular things in a book. Some topics are not, some topics are less available, some topics are easily available. Okay, but
Okay,
after
sir.
that the PK sir who is covered, he is basically the practical scenario. So for this one there is no notes are available.
Yeah, one. Okay, sir. And one more thing. What about analog lab, sir? Will we be doing all this op amps or will we be doing all those Bluetooth subsystems?
Mm, mm, please repeat your question.
We are having analog lab one subject.
Yes, 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 yes.
So there will we be doing all this whatever we are studying right now, op amps and all
Actually, I
various.
don't. Actually, I don't have any idea till now about the analog electronics there. So I will confirm till Monday, Tuesday. Okay, Tuesday we have a one more session. So till that, in that I will confirm you what is the basically cover in that.
Okay, sir.
Okay,
Thank you.
because some other professor will be taking. So that's why I don't have any idea.